And today, we're going to be looking at something slightly different. So as a reminder, when force is constant, work is given by F dot D, otherwise known as FD cosine theta. And the work energy theorem says that the kinetic energy of a system changes based on the work or equal to the amount of work done on or by the system. Now, we've all played with the springs when we're children, or rubber bands, matat. So, one of these. Yeah, we all played with one of these when we were children. Now, if you remember, not pasting. If you remember, when playing with this thing, we usually put it on our wrist. And if you pull it a little bit and let it go, pretty much nothing happens. Maybe it tickles. If you pull it a bit further, it might start to hurt a little bit. And if your friend decides it's a fun thing to do, your friend would pull that rubber band quite a bit and then let it go, and then you're going to scream and try to get him or her back for that. Now, the key point here is this is the same rubber band, but the amount of pain you were experiencing depended on how much that rubber band was pulled. Salim, try disconnecting and reconnecting. Maybe it will work. Oh, wait, he says he cannot hear, so me saying what he should do is probably something he's not going to hear. Okay. So why is it that the same object, the spring, is hurting us differently at different times? Well, a spring force is a slightly different type of force, or a rubber band force is slightly a different type of force from what we have been working with so far, in that it is a variable force. It changes depending on circumstances. Now, we call it a spring force because it is mainly, it was the examples we use have to do with springs, and it was at the very beginning, it was found from while working with springs. And it has a particular mathematical form, which we're going to take a look at in a second. But many forces in nature have this form. So for example, the example we gave at the beginning, the rubber band. It's not a spring, yet it has the same force. Take all of this away. And then take all of this away. And then take all of this away. And we can start again. Now, here we have a spring horizontally, so we don't have to worry about gravity or anything else. And it's attached to a block. This center part of the block, where I have indicated by x equals 0, is the natural position of the spring to be at. Okay, so you can take it this, or you can take this point right at the end of the spring, okay, and call this x equals 0. It's up to you. And we call this the natural position, or the equilibrium position, or the rest position, or the normal position. Give it a name that you want. Now, when I pull that spring, I exert a force to pull it and move that exact same point. So whether you choose this or this, you decide which point it is. You move it from x equals 0 to some other x equals x. Yeah, there's a delta x. You have moved it a little bit. Now, you have exerted a certain amount of force using your hand, for example, to the right to pull it, but you feel a pull back as if the spring doesn't want to be there. Yeah, you feel that pull back, whether it is with a spring, whether it is with a rubber band, you feel it wanting to go back. And the only thing keeping it in place is because you are holding it with your hand, exerting that amount of force. And this force that wants to take it back to the x equals 0 position, to the equilibrium position, yeah, is what we call the restoring force. Okay, because it wants to restore it to the natural position that it is very, very happy at. And this force, turns out, has a very, very specific format, and that the restoring force is given by F equals minus kx. And the exerted force is F equals kx. And you know this because you know from playing with springs or playing with rubber bands that the more you want to pull it, the harder it is, right? And the reason for that is it's harder because your x is bigger, and that means your F needs to be bigger. Now, on the other hand, instead of pulling the spring, I can push the spring to the inside. And the same thing happens. I am pushing it, I'm exerting a force against the spring, and the spring is pushing back. As soon as I remove my hand, it goes back. And that is the restoring force. Again, here the directions are opposite. My extending is minus kx and my restoring is kx, but it's in the opposite direction. That's the important point. And we have the letter k in all of these equations, which is what we call the spring stiffness constant. And what that means is how much of a pain that spring is. So, you know, some springs are really easy to compress and stretch. Some are very, very tough and very, very strong. Yeah. Your mattress has nice springs. When you jump on bed, it's very springy. Your car suspension system, however, if you try to jump, is not going to be as nice and accommodating as your bed springs. It's not going to be as comfy and nice to jump on. So my question is, okay, or actually before my question, let's summarize what we've said so far. The spring force is given by Hooke's law, F equals minus kx or minus kd, where d is the displacement. The negative sign represents that the force is always opposite to the direction of the displacement. K is a measure of how stiff the spring is. And this force is variable. As we can see, it's a function of position with a linear relationship between force and displacement. So for a spring along the x-axis, we can write Fx equals minus kx. Y-axis, it would be Fy equals minus ky. And in 3 dimensions, we can write Fr equals minus kr and do it all with vectors. So far, so good. Any questions?
Yeah, it's
Okay. Now, I have a question for you. When we were calculating work earlier, we said it's F dot T, or Fd cosine theta, and force was constant. So it was rather simple, right? We took the force 10 newtons times the distance 10 meters, 10 times cosine theta, done. Yeah. But here, now we said F equals Kx, which means that if I have a spring that is like this, and then I tend to stretch it all the way here, okay, from x equals 0 to x equals 10, if I do a table of x and force, x 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, My force, because it's F equals kx, okay, now k is just a constant, so for the sake of argument, let's say in this case k equals 2. Okay, 2 equals 2 newtons per meter. No, go back. My force is going to be what? 0. Force will be in newtons. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20 newtons, right? So my force is different at every single point. Which one of these forces do I plug in to calculate the work? If I want to do FD cosine theta, which force do I plug in? My distance is 10. Okay, but which force do I put in? So one person says 20, which is the final force. One person says none of them. One person says all of them. Okay. If I put 20, I will end up doing, let's say my force is exactly here horizontal, so we don't have any components. If I do 20, I will end up doing 20 times 10, 200, cosine 0 is 1, so just 200 newtons. But the problem is, 20 was only at the last step. Here the force was not 20, here the force was not 20, here, here, here. In all of these places, it was not 20, which means I'm overestimating my force. Amr says each one W total. Okay, so Amr, your suggestion is to do, 0, 0, 1, 2, 2, 4, 3, 6 cosine theta, 4, 8 cosine theta, 5, 10 cosine theta, and then add them all up. Is that what you're saying?
Doctor, we may take the average. In this case, maybe 10.
Okay. If we take the average, we are going to be underestimating in some points and overestimating in other points, but that is one solution. Okay, Madhur says final x minus initial x, but that is delta x. What force do we take? Amar's onto something when he said add them all up, find the work for each point and add them all up. But I have one question, Amar. What about this point? So if I zoom in, okay, if I zoom in, I will see that in here, I have 2.1, 2.2, 2.5, all the way until 2.9. So what is my limit? Should I do it at 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10? Or should I do it at each one of the point ones and then add them all up? What should I do? Okay, so just 2. So just 2 and 3. But then my force between 2 and 3 is still changing. So my force at 2.1 is not the same as 2.2. It's not the same as 2. It's not the same as 2.5 and 2.9. Yeah. So we are more accurate. So option 1 is to take the average of everything. Option 2 is to go slightly more zoomed in. So we go 0, 5, 10, or 0, 10, initial and final. Option 3 is to take units 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then we have another option where we can, you know, zoom in further at 0.1, 0.2, 0.3. We can also take the average between each two, but whenever we take the average of something, we are losing a little bit of accuracy, okay, because we're just looking at the average. Yes, if it's perfectly distributed, that works. If not, then that's a bit of a problem. Turns out there is a solution. So just like Amr said, we take 1, 2, 3, 4, 5, 6, but then we go one step further. We go 0.2, 0.1, 2.2, 2.3, 2.4, all the way, you know, 0.1s. Then we go even further down. 2.01, 2.02, 2.03, 2.05, and so on and so forth. Then we can go 2.001, 2.002, 2.003, and so on and so forth. And eventually, yes, exactly, Mariam, to forever. And what do we call it when we have an infinite sum over smaller and smaller and smaller intervals? When we have an infinitely smaller sum, what do we call it? Does anyone remember? Limit, yep, exactly, Laith. And when we go to the limit to 0, what is it called? When we add an infinite sum with the limit going to 0, so when I do the sum from I equals 0 to infinity of xi di in the limit x goes to 0.
Derive?
Derivative, close enough. The other way around, sorry, someone was saying something?
Derive.
Derive, it's actually the opposite of derive.
وكامل.
It's integral. Yeah. When we integrate something, we are literally taking an infinite sum. Yeah. We are taking smaller and smaller and smaller portions. Yeah. So if this is the number line, for example, if this is my number line from 0 to 1, then what we're doing is we're taking this tiny, tiny portion, dx, in the limit, it goes to 0. Okay, as tiny as possible. And what we end up with is, we end up with an integral. So instead of saying f dot d, we say integral of f to dx. So we're going to look at it at every single point of time, from our initial to our final position. So let's plug it in. Spring, the force is minus f x dx. And let's actually do it on a whiteboard. Where's the whiteboard? Work is equal to f dot d. Tiny bit of work is equal to the force at tiny bit of distance, right? If I want the full work, then I need to integrate that force into that tiny bit of distance from the beginning of the distance to the end of the distance, right? What is force for a spring? What is the restoring force for the spring, we said? We said that the restoring force, F equals minus kx. So we have minus kx dx. K is a constant, so I'll take the minus k outside, and I end up with x dx. What's the integral of x dx?
X square by 2.
Yep. X squared over 2, which means I end up with minus k xf squared over 2 minus xi squared over 2. Then I'll open the brackets, minus and minus. So I end up with k xi squared over 2 minus k xf squared over 2. So from this, we can see that the work can be either positive or negative, and it depends on the net energy transfer. Yeah. Now, as we said, the zero position, the natural position, the equilibrium position is what I call the happy position. This is the normal position. This is where the spring is happy to be at. Okay, and this is where the spring wants to be at. So let's say you want a favor from your friend. You want to borrow some money, you want them to help you out in something. What do? You usually take them to somewhere where they're comfortable, right? And then you ask them for that favor. We do the exact same thing here with the spring. Okay, if the spring comes closer to its initial position, to its natural position, then it is a happy spring and it will give you energy. Your work will be positive. However, if the final position is further away from the happy position, zero position, then the spring is not happy and it ends up taking energy away. So negative work. Okay? So if this is my spring and I start here and I go all the way there, what is my work going to be? Well, it will be negative. It's not happy, right? You're going further away. So work is negative. However, if I start here and I go closer to the 0 point, okay, this is x equals to 0, then my spring is happy, and that is something positive. As usual, the work done is equal to the change in kinetic energy. Okay, so whether we are dealing with constant forces or variable forces, the work done is still equal to the change in kinetic energy. So, for an applied force, the change in kinetic energy, final kinetic energy minus initial kinetic energy, will be equal to the work applied plus the work from the spring. And if the kinetic and initial and final kinetic energies are 0, then these are exactly equal but opposite. So whatever work you're applying is exactly equal to the negative of the work done by the spring. So you're doing exactly the opposite. It cancels out. Let's look at a sample problem, 7.06. Where is my PDF? Okay. When a spring does work on an object, we cannot find the work by simply multiplying the spring force by the object displacement, because there is no one value for the force, it changes. We know this. Okay. In figure 7-11, a cumin canister of mass 0.4 kilograms slides across a horizontal frictionless counter with a speed of 0.5 meters per second. It then runs into and compresses a spring of spring constant K equals 715 newtons per meters. So what will happen is it will collapse, it will compress until it momentarily stops. And then the spring is going to push it back. Okay. But when the canister is momentarily stopped by the spring, so at maximum compression, what is the distance d the spring is compressed? And this might sound like a very, very stupid thing, but I will tell you why is this a good idea once we do the problem. So initial velocity is 0.5, final velocity is 0, mass is 0.4 kilograms, K is equal to 750, and we don't know the distance of compression. What we do know is that the change in kinetic energy is equal to the work done. So this should be very easy. The spring work is half kxi minus half kxf squared. This is xi, and xf will be my d. We don't know where d is. Okay. My delta k is kf minus ki. What is my final kinetic energy? 0, since it stops. Velocity is 0, so half mv squared is 0. My initial kinetic energy is half m 0.5 squared. Okay. And if I substitute all of this, okay, this is 0, this is 0, I end up with 0 minus half mvi squared is equal to minus half k d squared. We know m, we know vi, we know k. The minus halves cancel out. We can find d. Right? The di in this case is going to be what? Going to be 0.4 divided by 750, square root that times 0.5. So it's going to be 0.01 meters, which is a tiny, tiny amount. Now, I have a question for you. Is this kind of calculation useful in anything in real life? ولا مضيعة وقت? We're just doing it because we're bored and we like to do physics. Anyone? Okay. If you say it's مضيعة وقت, okay, fine enough, I can't ask you anything. But if you say it's useful, can you think of a way where this is actually useful in real life? I can tell you for sure that every single one of you, without exceptions, is betting your life on this thing on a daily basis, multiple times per day. Okay, car spring. The car suspension has springs. That's one example. Yes, that is correct. How many people? Okay, let me ask the question another way. Is there anyone here who does not get in a car? كلكم راكبين سيارات؟ كلكم تركبون سيارة يوميا تروحوا من مكان لمكان؟ Yes. في حد ما يركب سيارة في حياته؟ Okay. You all know about something called the airbag?
Yes, you know.
Yep. How does the airbag work? Have you ever wondered why لا سمح الله إذا السيارة دعمت في شيء بسيط الairbag ما ينفتح صح؟ لكن إذا الحادث كبير لا سمح الله الairbag deploys. Right? How does the airbag know when to deploy and when not to deploy?
There is sensors on the car.
Okay, and how do these sensors work?
استشعار قوة الصدمة دكتور.
So what happens is, say this is your steering wheel, right? صار لي زمان ما أرسم لكم الموناليزا. So I missed that. This is your steering wheel. And your airbag is usually right here behind the steering wheel. Okay. And what happens is you have a spring here, which is of quite a high spring constant. So you need a very high amount of force to compress it even a tiny bit. And of course, on this side, you have the front of the car. Now, what happens is here you have some chemical component and some pyros that get activated. Now, what happens is if you are in a tiny accident, this thing, the D, the compression, is quite low. So nothing happens. If, however, you are in a rather higher, bigger accident, the damage is more, the force is more. So this thing compresses even more. And when it compresses up to a certain degree, it pulls a pin from this. And the airbag deploys. Yeah. So you're literally betting your life on this thing every day, working or not working. Amar, well, this is not supposed to be سماعة, but believe it or not, السماعة تشتغل بنفس الأسلوب. Only, instead of force of an accident of the car, it uses your sound waves, to censor the pressure. It senses the pressure from your sound waves, and there's a spring in it, which goes up or down, okay? Whether it's a microphone or whether you're talking about a speaker, okay? You have a percussive surface there with a tiny spring. And that spring, depending on this amount of force, it compresses or it stretches, and it measures what you're saying or makes the sounds you're hearing. So this thing actually has a lot of potential and a lot of applications. Okay. It's been some time since we've done a PIQ. Let's do a PIQ on Moodle. So we're doing PIQs number 14, section 7.3 to 7.4. I'm going to the question. We're not there yet. And you should see the question in 3, 2, 1. I'll give you a few minutes to try it out. In designing a spring-loaded cannon, determine the spring constant required to launch a 2-kilogram ball with an initial speed of 1.2 meters per second from a position where the spring is displaced only 15 centimeters from its equilibrium position. Okay, so should be appearing to you. Take your time. So you have relevant equations are F equals to minus kx, and you have the work equals half kxi squared minus half kxf squared, and you have the work energy theorem. Okay. Let's see, is everyone done? 9 people haven't answered yet. So let's see. 63 people said 130 Newton per meter, and about 4 people each said any of the other answers. Okay. And the correct answer is indeed 130 newtons per meters. Well done. Very well done. Job very, very well done. Okay. So this is my cannon. And it's based on a spring. Now, it goes back 15 centimeters, 0.15 meters. Initially, it has no velocity. And then it is released, and we require the final velocity to be 1.2 meters per second. Well, the work done by the spring is xi minus xf, half kxi squared minus half kxf squared. And my kinetic energy change is going to be half mvf squared minus half mvi squared. Well, let's start making it simpler. My x final, okay, why is this not working? My x final is going to be 0. My velocity initial is 0. So I only have 2 terms left. Work equals delta k. My work done is going to be half kxi squared. So half k, and my x is 0.15 squared. My final velocity is half mvf squared. That means I can rearrange these two equations to get k. Okay. Well done. I'm really happy that pretty much everyone has got this answer correctly. Let's do a quick comparison. We'll do another question. Abdul Dawood, try to refresh the page. And if not, then put your answer down in the chat or something. Or at least try to do it on a piece of paper. Okay. So we have another question. Blocks A and B have masses m and 2m respectively. Block A compresses a spring by a distance x and then is released. After separating from the spring, it slides across the surface where there is some kinetic coefficient, and then it stops. Now, when it does the same thing with block B, which one of the following is correct? Block A has mass m, block B has mass 2m. Give it a go. We're comparing the distances they are going to slide. Block A slides 1/4 of the distance of B, 1/2, same, or double, or 4 times even. The idea is still the same. Sorry, Abdul Wadud, not Abdul Dawood. I'm looking at it from my phone and the font is very tiny. Okay, let's see how have you done. Okay, we seem to have an overwhelming majority that says block A slides double the distance that block B slides. Okay, fair enough, fair enough. Let's take a look. We have two blocks, A and B, mass M, mass 2m. They are both compressed with the same distance, so the work done by the spring is exactly the same. The work done of the spring only depends on how much it's spring, not on the mass of the thing that springs it. But then that same amount of work is transferred to kinetic energy. One of them has double the mass of the other, right? Now, if the work done يا أخي ما نريد مسابقة، لا نبغى مسابقة صباح الشباب ولا مسابقة حلم ولا نربح المليون، فكونا من ذي المسجات. Okay? So if the work done by the spring is the same, okay, then we have the same initial amount of energy. Okay? We start with the same amount of energy, and how far we go depends only on one thing: how much friction acts on it. Now, we know friction depends on the normal force, which depends on the mass and weight. Okay. So I don't like this slide. It's not very useful. Let's do it ourselves on the whiteboard. What do you think? So we have the same WS. WS okay. So WS is the same for both. This will be my initial energy. Where does it go? It is dissipated by friction. Okay, so friction for A is going to be mu k Fn, which is mu k mg, right? Friction for B will be mu k Fn, but for it will be mu k 2mg, which means that one block will go twice as far away as the other. Yeah? So pretty much everyone was correct. Yes, Muhammad, that I'm trying to include more and more of these where possible. Okay. I'm trying to include more of these as much as possible, especially for more complicated questions. So it's easier for you to revise later. It's interesting. So it shows it to you now, immediately after the question. That's nice. That's really nice. So works. I'm glad you're happy with that. Okay. Okay. Now, let me. I have way too many tabs open. It drives me crazy. So many folders and files and tabs. Okay, so we'll take a quick look. So what we have done now with the spring, okay, is look at what work is done by the variable spring, which is of the force itself. But this is not what we did is not special only for the spring. This is the same thing that we apply to any variable force. So we can have many variable forces which are not spring variable forces, which are different variable forces. Okay, we have an external, we have a force which is variable. So if it changes with position, for example, it is equal to the area under the curve, which is equal to integration, which we just said. Okay, now we said all of this. Now this is the important point. Okay, what we did for f of x dx and integrated, we substituted f of x for f equals kx. Yes, but it doesn't have to be f equals kx. It can be any force whatsoever. Say, for example, we have this force. Force function 5x squared plus 10x plus 2. Can you tell me what the work will be? Anyone? No? So what happens is we integrate the function with respect to dx. So we end up with 5x cubed over 3 plus 10x squared over 2 plus 2x from xi to xf. Simple as that. Okay. What if I have something in 3 dimensions? So my force is not only in the x-axis, I have a 3-dimensional force, fx, fy, fz, and I am working in 3-dimensional space, so x, y, z. I have dx, dy, dz. What do I do then? How do I calculate the work? Well, the rule doesn't change. The rule is still W equals F dot T. dW is still equal to F dot dr. Nothing changed. Yeah? So we just simply do the dot product, F dot dr, which gives us Fx dx, Fy dy, and Fz dz. Because remember, according to the dot product rules, yeah, i's and i's just go away, and two different letters go to 0. So we end up with this. Work is equal to integral fx dx from xi xf, fy dy, yi yf, fz dz, zi zf. Same thing, we just do it in 3 different axes, and then we add them. And here's the important bit. What did we say work is? A scalar, right? Energy is a scalar, we said, not a vector. So when we take the dot product of f dot dr, what do we end up with? These 3 integrals. This thing gives me a number. This thing also gives me a number. And this thing also gives me a number. And when I add them up, my result is what? Just a number. Yeah, just a number, scalar. So I noticed quite a few people in quiz number 3 made this mistake when the question was on, on the dot product. Their final answer was a vector, which is not what the scalar product gives you. Yeah, this is very important. Your W is not you don't have wx in the I plus wy in the j plus wz in the k direction. You do not have this. You just have a single number. So, what time is it? 106. Yeah, we still have a tiny bit of time. Work kinetic energy theorem that W equals delta K with a variable force. We've done this with a numerical example and the canon bit, but now we'll do it here with the general bit. So if work is equal to f of x dx integrated, and just a general force, we don't know what a force is. It's not a specific function. What is F equals to? MA, right? Okay. This is a bit of a headache. Okay. So we are proving here that this is true for any general force MA, not only specific forces. Okay. MA can be written as m dv by dt because acceleration is the first derivative of velocity. Remember from chapter 2? Or chapter 2. Now I can rewrite dv by dt. Those of you who have done calculus know what I'm doing here. I can rewrite dv by dt as dv by dx v. أيوة عمر؟ Where is that? It must be W total, not just W. وين هذا عمر؟ Here you mean? Yes, W equals delta K. W is the total work. Yeah, W is the total work. Okay. I'll actually skip this slide because how many people here have not done calculus 1? Or how many people here are looking at this page and are seeing absolute gibberish? They have no idea what it's saying. All right. Since most of you seem to have understanding it, let's actually do it. So m dv by dt, by using the chain rule for changing variables, dv by dt is the same as writing dv by dx, dx by dt. We know that the rate of change of position, dx by dt, is velocity. So dv by dx comes here, and dx by dt becomes velocity. So I end up here. I end up having mv dv, the dx's cancel. The work is equal to integral of mv dv. M is a constant, it goes outside. We end up with half mvf squared minus half mvi squared, which is final kinetic energy, initial kinetic energy, which is delta K. let's call it a day. We have covered quite a bit of material today. So let's call it a day, and we continue next week by a quick overview of power, and then continuing on with chapter 8.